It's my pleasure to start the Yip lecture for CMSA, Center of Math Science and Application. Dr. Yip was very generous that he contributed a large sum of money to form this lecture series. And he likes philosophy, science, and all that. So I'm very happy that he actually fly all the way from Hong Kong to attend this first lecture.
How are you?
He'd like to say a few words before the whole lecture. So, Dr. Yip.
Thank you. Where shall I stand? Yes. Professor Yao, Professor Galison, and honorary guests, it is an honor and privilege for me to be asked by Dr. Yao to contribute to the Yip lecture series at the Harvard Mathematical Center. It all began when Dr. Martin Mim, well, he should be here, good, wonderful. When Dr. Martin Mim and myself, we were fellow residents at the Massachusetts General Hospital in the early 60s. So that gives you an idea of my age. Well, Dr. Mim works at the Brigham, and he's a dermatopathologist. And he was very keen that we endow a chair at the Brigham for Harvard Medical School, and I did so with him in 2015. And then, because of that, Brigham hosted an evening meeting for me to give a talk on our theory on consciousness at the Harvard Club in Boston. It was a East Meet West series, and Dr. Yao thought it should continue under his auspices at his mathematics department, both in Cambridge and at Tsinghua University in China. I'm very glad to do so. It's a very great honor. The aim is to integrate science with philosophy, and you can see today that he has started the series with a most distinguished speaker in the person of Professor Peter Galison, who will speak about the very hot topic of black holes. A picture of that is in every newspaper all over the world. Now, before I finish, I would like to congratulate Professor Yao again for his 70th birthday. And within 2 weeks, he will have a celebration and also a symposium. Again, I would say that I'm very glad to be here at Oxford Street, because in the early 60s, I lived for 4 years in a little street called Crescent Street of Oxford, and they were very happy memories. So I'll now hand the podium back to Dr. Yao.
Well, thank you very much, Dr. Yip, and I'm sure we will cooperate more and more between Hong Kong and here. Today, we have the first lecture with one of the most spectacular discovery in this century, and also is given by one of our greatest professor, Professor Peter Galison, on the philosophy of the shadow. It's really the best timing, but I think he probably purposely make the timing for that purpose. Anyway, so Peter, so you will start. Thank you.
Thank you. I think I'm good. Yeah. So first I want to say how grateful I am to my senior colleagues at the Black Hole Initiative, to the junior colleagues I've been working with over these last years. It's been one of the greatest experiences I've had in the university or anywhere, and I'm honored to be a member of the Event Horizon Telescope and the Black Hole Initiative, so thank you. Black holes are among the strangest objects that we know. They seem paradoxical in every way. They're the simplest objects and the most complicated objects. They can be as small as you like. They can be the biggest objects in the universe. They can shoot jets across clusters of galaxies. They can change the way stars are formed. And yet, they can be the darkest objects. They're the lighthouses of the universe and the most mysterious ones. I want to begin by reflecting on this moment of a shadow teaching us so much about the universe. One thinks of a time of witch hunts and a time in which the shadows of a celestial body transformed our understanding of the cosmos.
Galileo discovered the mountains on the moon by looking at shadows. It was one of the first things that he did with his telescope. And as he looked there, he saw the variations of light and dark and the shadows cast across the terminator separating the light and dark parts of the moon. These are his first initial sketches of what he saw, and then published it in the Starry Messenger that left us a legacy of the shadow and the cosmos. The shadow that we're looking at in the black hole is a little different. It takes the light in back of the black hole, essentially, and bends it around so that we see that in relief. We see the shadow of all of that light that's cast around it. Einstein predicted, and it was confirmed in November of 1919, that stars had their light gently bent by the sun, as could be seen during a total eclipse. This is a much more severe bending, one that can give rise to the ring that we see so characteristically in the image that has gotten such wide circulation over the last days. I'd like today to talk about what an objective image is. What do we want from an objective image in science? What is its history? How does it govern how we think about what we want from an image of science? And then I want to get to the image of the black hole itself, M80, at the center of the Messier 87 galaxy, one of the biggest galaxies that we know of, and to talk about what it means to satisfy ourselves that we're looking at a real effect and not at an artifact. Back in the 18th century, and I'm going to be enormously schematic here, building on work that Lorraine Daston and I did some years ago, that people did try to represent nature to get the best right depiction of the world that they could. But even Cheselden, looking through a camera obscura at a skeleton hung upside down so he could see it right side up, fixed it. He thought you had to mend that which was wrong by using pencils, needles, and placement. When Goethe talked about the Urpflanze, he said that no particular animal could be used. You needed to abstract, you needed to part the curtains of experience of any particular individual. No one wanted to depict the half moth-eaten clover outside this building. They wanted the clover as it should be, even if no particular instance corresponded to it precisely. When Albinus sketched in the 18th century this skeleton, he idealized not just putting it in a dancing form in front of a rhinoceros, but also to perfect those things that he said had to exhibit a more perfect pattern than could be formed in any individual. So in a cartoonish way, you could think of the notion of a truth to nature, a kind of this parting of particulars to see the ideal form behind it, as something that a sage or genius could do, like Goethe, Albinus, or Cheselden. It was an image that had the status of being metaphysical, behind or above any particular physical instantiation. The practice is one of intervention, to begin to modify with pencil and needle and all other forms what you were seeing. And the ontology, that is to say, what was represented, was a universal. In the 19th century, a different kind of morality began to govern, or ethics of image making began to dominate. You had an attempt so that even when people knew that something was wrong in their image, for instance, in figure 2 here, this is Otto Funke's depiction of crystallized blood, that lower part that's yellowing, he knew was chromatic aberration, distortion by the lens. He knew that when one crystal stood in front of the other, that it looked bent like your arm in water, but he depicted it anyway. He said, in this I must be faithful, conscientious, and draw even the deceptions. Albinus would never draw a deception. Goethe would never be faithful to mere appearance when the mind could penetrate beyond that. It led to crises for individuals as they made this transition. Arthur Worthington, whose work on droplets still governs much of how we understand fluid drops today, at first only drew perfectly symmetrical forms of the splash as a milk or water droplet hit the ground or hit a surface. And it was a shock to him when he first began to realize through new techniques that these were anything but regular, The same was true in snowflakes. People would draw snowflakes into the late 19th century in perfect hexagonal symmetry because they knew, or thought they knew, that that was the true form of snowflakes. In fact, one of them, so it's very hard to photograph or to represent a snowflake under bright lights because they melt. But they would draw one arm, and one of the chief snowflakers would hand off his drawing to his wife, who would then fill out the other 5 arms by symmetry. So, but this new form of representation in which the scientific self was more of a worker tending a machine to make identical forks or bullets or knives or whatever it was, had as the image a mechanical form. Your job was to allow nature to write itself to the page, to draw itself to the page. Even before film photography, the practice was one of algorithmic or mechanical transfer, and the ontology was one of individuals. If I depict this skull, I mean this skull of this person which now sits in case 42 of the Oxford Museum. It did not mean the skull as it should be, but the skull as it was in a particular instance. Skipping ahead, continuing my cartoon representation of history, in the 1900s, people began to realize that this automatic transfer, this protocol-driven transfer of nature to the page led to all sorts of problems. For example, when people first were making MRI images, there were these artifacts that arose, and in fact, they did a lot of back surgeries, I gather, that were nothing but a misunderstanding of how the Fourier transform worked. But there was a sense, as these methods got more sophisticated, that you had to intervene, not because you were a genius like Goethe or Albinus, but because you knew how the machines worked. And your expert judgment was necessary to get a right depiction, in this case, the magnetic fields of the sun. And people said explicitly a certain subjectivity to these charts is necessary, because otherwise the artifacts of the machine transfer would simply overwhelm, and you would not be able to learn anything. So in this case, the scientific self morphs to something else. Now it's an expert, not a sage or a genius, but someone trained to be able to do this kind of work. You can learn to recognize the distinction between different disorders of the heart or the brain as you learn to read an electroencephalogram or an electrocardiogram. The image is one that's interpreted now. The practice is one of conditioned or trained or expert judgment. And the ontology is one of a collection of objects that represent the best we can do. So, but these accumulate like stratigraphic layers. Again, schematizing. Truth to nature begins in the 1730s or 40s, but it continues. And we still have uses, and I'll talk about some of them, for where we want to idealize in this way. Mechanical objectivity, which begins in the 19th century, layers on top of that. Now you have both truth to nature attempts to extract beyond experience, but also this form of algorithmic or protocol-driven mechanical objectivity. And then in the 20th century, trained judgment as we begin to value the expert and what the expert can do. I want to see what we're doing with the black hole image and what we've been talking about all these years, as in a way combining these various strategies in ways that I'll come to in the time to come. So just to give you an idea of what I mean by layered and pressured, when people start to use idealized images in more recent times, it's not because they think they found a Platonic ideal. When Peterson's bird guide draws you a bird, the goal is to exaggerate certain features in order to be able to recognize on the fly, literally, what this bird is. When Galton takes all of these images of murderers in the London jails in 1878, it's not because there's any particular person that looks like that, but because he hopes that he can find the type. So he's combining actual photographs in a way to try to generate some kind of ideal. We obviously see that as rather problematic use of this idea, but whereas Peterson we continue to use. So these abstracted images continue to play in various ways even now. So at the center of our galaxy, Sagittarius A star is a 4 million solar mass supermassive black hole, and we have a good reason to think we know a lot about its mass by looking at the stars that can be seen orbiting around it. By knowing something about the properties of those stars, about the orbit, we can tell how much mass must be concentrated into a small area, and that, it seems, must be a black hole. So farther out, 1,000, 1,500 times out past the point of no return, the horizon of a black hole, we have visual evidence. With LIGO, one of the great experiments of modern times, we have close-in information but no image. So we've had to choose now between close-in information that is following the pulses of gravity waves as they move the mirrors on these huge laser interferometers, or images that are farther away. And the hope of the Event Horizon Telescope has been to get close in and an image near the Event Horizon Telescope and open to what we might find there in a way that only images can do. In order to make this kind of image, you need two things. You need to have waves that are able to penetrate the interstellar medium and to give you the kind of resolution that you need to be very tiny, millimeter waves, and you need a mirror, essentially, a telescope the size of the Earth. Well, that's hard to get, but you can take telescopes in various parts of the Earth and combine them to create a virtual telescope of the right diameter. So now it's pushing on every limit. It's pushing on the edge of the planet we live on. It's pushing on the smallness of the wavelength, which requires new ways of storing information and electronically processing it and running your radio telescopes. And so but there's a further element that you need. In these 6 sites, 8 telescopes, you have baselines that essentially each pick up, are especially good at certain frequencies of their ability to pick up the image that's coming in. But happily, on many counts, the Earth is itself turning. And so each baseline, it's like having an antenna that's swiveling, and as different parts of it face the black hole, it picks up and fills out the mirrors, so to speak. It's as if you had a string of tuning forks, old school tuning forks, and you were trying to pick up a musical tune. By itself, you would have very fragmented information, just those particular frequencies. But if you moved the tuning forks towards your target and pulled it away, you could use the Doppler shift of moving towards and away from it to pick up other frequencies, and so fill out your knowledge about what that tune might be. So there are two problems that face two opposite problems, a kind of Scylla and Charybdis that face us in this project. One we'll call the helm of Hades, which was, as you remember, Perseus and Athena had this helmet that they could put on that made them invisible. And the problem, because we're sampling such sparse bits of the image from this distant black hole, is that we might not see anything at all. It's there's all sorts of things that cause noise in the signal. It's sparse. We only have fragments. And the first danger is that we wouldn't be able to get anything from this image at all, even though we had a nice little wavelength and a great big antenna. So this produces, from all these different sites, petabytes of data, 4 or 5 petabytes of data that have to be shipped in giant crates back to a place where they're correlated in Haystack Observatory that's run by MIT, not far from here, and in Munich. And this data is then reduced in various ways, sampling from it, to get an image. But then you have this problem: how are you going to deal with the sparse, noisy image that you had? Well, the tried and true method of radio astronomers for a long time has been to use a method called clean. And what they do is they say they know if you have a single star, for instance, and you have a fragmented set of antennas that are only partially covering all that you would like covered, that you get a lot of noise around the star. So now you know what a point would do given what you actually can measure. And so you can take that information and use it to take an image. Suppose you had a galaxy that you were looking at, and you would take each bright spot and use and subtract all the junk that's around a real point source. So you would use this to clean up your image, to get rid of all the artifacts that are produced by incompletely sampling from the plane. And this takes great skill, and it's something that astronomers have become very good at doing. But because it's skillful, because it needs, as people say, a knowledgeable user to get this right, there is a danger that it depends on the idiosyncrasies of the observer. And furthermore, it can be difficult if you have an extended source, because an extended source, which is not made of point sources, can be more complicated to handle with the clean method. But the clean method remains one of our great reliable pillars for this kind of thing. So here's the second noise, a big noise source for any kind of signal, is the weather. Even after these poor photons have spent 53.5 million years getting to us, they can lose themselves in the clouds that are blowing overhead. So you need essentially good weather across the entire planet, which is a lot to ask.
And we're pushing the technology as far as we can go. So what are the pinch points here? What are the decision points here? It's really just LMT and SMT. And we're going to have to make a decision based at South Pole, just based on what we know now, which is that they might have pointing issues. Okay, so let's take one last look at this current readiness page.
ALMA apex, we said, is still less than 0.03. This is 0.04. Pico, we just said is 0.2. Okay, good.
I think it's going to be amazing for all of us to be able to see a black hole.
I mean, based on what we saw a few hours ago, the weather is good.
But beyond that, there is a very definitive prediction of general relativity in terms of what shape and size the hole and the ring around that hole should be.
So the weather was good, and we got amazing data in 2017 in April. But then there's a question of what other methods we might be able to use. And a new method, or not a new, but a method that's been highly developed by the imaging group, which is about 60 or 70 people, many of whom are here in this room, was to say, we know certain things about the image. Can we use our assumptions about justified assumptions, we hope, about what the image might be like, to help us answer the question, what is the image hiding behind this noisy, sparse data? It's a little bit like this. If you had a bunch of blue points and a bunch of red points, and I said, draw a line separating them, you would say, rightly, that's not a well-determined problem. You could say to me, what's the best straight line? And you could get a high school student to solve that. You could say, what's the best circle, a fragment of a circle that would do it, and you could solve that. A little more difficulty, not much, and so on. So with prior knowledge, it becomes a well-defined problem. But what are those priors? What must you assume such that you can resolve this in a way that you hope won't predetermine the answer you're getting? You don't want to assume what you're trying to demonstrate. And that leads to the second problem, the spring of Narcissus. Narcissus, as you recall, looks into the spring and sees himself. And that's the other nightmare. If one nightmare is the helm of Hades, the other is the spring of Narcissus. You want to make sure that what you're assuming to make this a well-defined problem in creating an image that you can count on, that you don't push into the image itself assumptions that will make it so. So that's our problem. How do you put in enough assumptions to get an image out of this noise and sparsity and yet not push onto the image what isn't there? So one of the first method that was used was a kind of socio-epistemology in a way. It said, let's get 4 groups, don't talk to each other. They use all the skill that they can muster. It's just anything you can put into this that will be able to get a good image out should be applied. And we distributed a set of data to each of the groups, that's the same data to each of the groups, and said, what do you see? Come up with it. And then got together and saw how well they corresponded, and did this over and over again, trying to get to the point where these various different methods would coincide. You would have these ground truth images, something that was put in synthetically, and then each of the groups had to do it. Some would be astronomical, some would be geometrical, some would be something like what we thought the black hole might look like. Some of them could be just pictures taken at random off the internet. And you began to see this and see how they did as more noise was added to the system. Some of them began to fall apart. Some of them kept sharp. And so little by little, we could learn what was going on. You could then ask the same team a set of, give them further challenges and get them to refine what they were assuming in order to see if they could improve their rendition of what these might be. So these hackathons, these image hackathons, would include even things like Frosty the Snowman. I mean, the whole point of trying to make an image of the black hole was that you didn't want to assume that you knew what it was going to look like. Now, it probably wasn't going to look like Frosty the Snowman, but you wanted to be prepared to image something that didn't look like what you expected. And we tried simulated black hole images. We tried astronomical images. We tried natural images, like this person with a movie camera at the upper right. There's methods that Ramesh Narayan developed to explore these questions and really try to understand when they broke down, what kinds of artifacts could get produced by the clean method, by this regularized method, this assumptions of priors, the so-called maximum entropy methods. Did they put peaks where there were no peaks? Did they lose peaks where there were peaks? What kind of situation could be there? And so these sorts of questions were agonizingly difficult, trying to get this. So Ramesh has a line from one of his papers, which I like, which says, if we obtain very different restorations, the places where they agree should tell us what we can really believe. And so trying to compare the clean method, the tried and true astronomical method, with these new regularized maximum likelihood method, that's what we wanted to know. How much could they agree when they didn't know the original source? And could we keep them apart long enough to allow them to work independently? So here's Daniel putting up his helm of Hades here to prevent anybody else from looking in on the group and we, making sure doors are closed. You couldn't say anything to people. You couldn't talk to your colleagues. This is intra-collaboration, even within the imaging group, keeping secret from each other what we were seeing. So this is more of the colleagues who are in this, many of them are in this room, at the moment when one of those groups first began to see.
Shut, close the door. Okay, are we ready?
Wait, what is happening? Like,
We're trying to make an image right now.
Can we just like pace things a little bit?
Okay. Well, no, first of all.
When we...
So the groups then got together in the third week of July last year, and we began to see that we all were getting a ring. So that was an astonishing moment, and sort of as if we'd finally tracked down the snark. We put it on the screen and took a picture. So this was 24 July 2018, but you might think that was the end of things. That was actually when the panic began, because now we had an image that we agreed on, and the question is it real? Is there any way that we could all be pursuing a pipe dream? We all know many cases in physics and other branches of science where our expectations drive us to see something that we hoped were there. It's something I worry about a lot. The first book I wrote was called How Experiments End. It's about how theoretical presuppositions lead people to find experimentally things that they expected to see. So I was really worried about this. And we used to, I've often thought of epistemology as a kind of response to a fear that that there was something that was going to escape you. It could be the fear, for instance, that you would be deceived by a particular skull or a half moth-eaten clover or an aberrant crystal, and the truth to nature was an attempt to get around that. The fear that mechanical objectivity was responding to was that everybody would consider themselves a Goethe or Albinus and say what they thought things really should be like. And couldn't there be a way to mechanically or procedurally get around that idiosyncratic desire to see what we want to see? But here, that epistemological fear, when I had first written about that, I thought of that as somewhat abstract. But now we all were really worried about it, because this really was terrifying. And that's what went on between the 24th of July and 9:07 a.m. on the 10th last week. It was trying to make sure that we weren't missing something. So one immediate question was, are there ways to compare these different techniques, the clean techniques and the regularized methods, by, for instance, blurring the different images to the same level of accuracy? So you're not assuming that you can get things more accurately than were merited by the data. And so blurring these and averaging them, we began to come up with particular images and to see how they matched on the different days, to see whether there was change over time, to see how different they were from each other. And so the average from each day looked like this, and we're pretty close. So each of these tests, we would try saying, well, what if one antenna was doing something screwy? What if we, one at a time, took out the antennas, took number one out, looked at the image, put it back, took number two, took that out, put it back, and made an image, and so on. And there were many, many such tests. Another thing was, so we had this method that depended on expert comparisons. But then you might say, okay, suppose, sort of playing backwards from historical development, suppose that or just responding to that same fear, suppose you thought that the experts might have put in too much of what they knew. Is there a way that we could more mechanically or algorithmically proceed? And so one question was, could you change the parameters, the sort of setting on your camera, so to speak, in a way that would search out all the different combinations and see if it still reliably could produce an image? So starting with images where we, unlike the black hole, we knew what they were. We made them. So synthetic images like a ring or a crescent or a disk or two spots next to each other, and began to explore that. Now there are little knobs that you can turn, so to speak, in the code. One might be how much you expected there to be sort of flat regions with sharp edges. Another might be the total amount of illumination and where it was. And another might be images with smooth edges. And so we would try to change these and these things in all sorts of ways to see if we still got the ring and the shadow in it. And I don't know how many total were in the parameter search, but certainly tens of thousands, maybe hundreds of thousands. How many? Anyway, 100,000. So a lot. And so out of those images, out of looking at what gave you good results on the synthetic data, you began to say, okay, here are the settings that are reliable ways of making an image match what the original source was. And you could begin to look at the data from M87, from the supermassive black hole, and to look on the different days and with the different ways of proceeding, with clean or other methods, and to see what you got. And we still get the ring. Then there was a question that arose, should we try so to speak, the third avenue that I've discussed, this idea of truth to nature, of some image that would stand for all the images in a way. And we tried various things, various sophisticated mathematical approaches, and then just decided, let's try to average the images, not very sophisticated. And why would you want to get a single image? Well, we had big debates about this over the last months. And one of the reasons had nothing to do with the science. It was, we have a collaboration with 18 countries, 59 institutions, 207 collaborators, and nobody wanted to be left out of the image, right? So they didn't want the image to be made by person 1 or 27 or 206. So you wanted to average, and then in a way, there was a kind of collective achievement that would be there. That never moved me particularly as a scientific argument, I have to say, but I understand it psychosocially, and it was one thing that was very often discussed. Another would be to say, would the image that came as an average look pretty much in a qualitative way like each of the different constituent images that were being averaged? Now, why would that be a problem? Well, suppose you had two pictures. One was Mount Everest, and the other was a valley that looked like the opposite of Mount Everest, only dug into the ground 5 miles deep. And you took their average, and you got something that looked like the desert, flat. That would not be a good outcome, right? If you took that desert-like image and said, this is the average of my other images, you actually don't look either like a 5-mile hole or a 5-mile peak. So we wanted to make sure that that's at least, seems to me, that's a plausible reason for looking at the average. The other is that it's just conservative. It just says, let's not get too fascinated with quirks that are on one image rather than another, but rather see what the average image does is it values that which is in each of the images. So that might be also, that's sort of those are, numbers 2 and 3 are reasonable arguments, even if one doesn't move me. And so we came up with this image that you know, and that's what went onto the screen at 9:07 all over the world. That there were these similar. This was in Washington D.C., but there's one in Brussels and in Singapore and in China and Japan, all over the place. Chile had one, and it was an agreement that everybody would at 9:07 would show the image, not before, because whoever showed it first could scoop the others, and that was unacceptable for everyone, both in the collaboration and for the nation states that supported the research. So what is this image? This image, in a way, is a combination of all of these strands of image epistemology that have wound up over the last several hundred years. There's trained expertise, this idea that you would have groups, 4 groups, using these different methods, using all the skill they could muster and no information from what the other groups were getting, and then to compare them and to see what might be held in common. You had mechanical objectivity, this idea that there should be a way that escaped from the vagaries of personal preference or training or tradition that would allow us to explore the wide range of possible parameters, to train up on things that we knew because we made them, the synthetic data, and then to apply them to the thing that we didn't know. I mean, in a way, the problem is, if you want to test a camera, a lens, the camera body, and the film or the charge coupled device that's in the back of the camera, you try to test them separately, and you try to test them on things you know. You put up a test chart on the wall and test your lens with a known camera body and a known film or electronic back, and then you take the camera body and you use a known lens and a known film or a known back, and the same with the film. But we were in a situation where you had a new instrument, new methods of making the image, like as if the new programs were being put on your charge coupled device at the back of the camera, and an object that no one had ever seen. And that's what made the thing so fearful in an epistemological sense, because everything was happening at once. And so any tricks that we could figure out to try to isolate these different components was absolutely crucial. And so the problem of gaining and securing this knowledge was, try out on known sources, try on synthetic data, have these image hackathons, try varying the parameters. All of these were designed to try to get at the characteristics of this new method of making an image as insofar as it could be done to give us confidence that if we did get an image of the black hole, it would be something that we would be able to consider reliable. And then the consensus image, which is a version of truth to nature, was itself a part of this. Not at all in the tradition, an exact version of the metaphysics of the 18th century, but under the pressure of all that had happened since then, still and nonetheless an attempt to extract a single picture that was, even if not as detailed as it could be, at least it was something that, in which would hold our belief as reflecting something in nature. So what did Galileo do? In November and December 1609, he saw these shadows on the moon. And then he made a movie. I mean, that's what this is. These are the days in January 1610 of the position of the moons of Jupiter. And he's looking at them. These are like frames of a film. And he's watching them change. It's their changeability and the motion of these stars, as seen as you go down the month of January, that he began to see that there was something else to be done, and that this telescope offered a completely new view of the solar system. It was tremendously important. It had huge cosmological significance. Now you had a completely clear refutation of the view that the planets were transported on crystalline spheres because these moons would shatter it as sure as the day is long. And that became one of the things. He named them after his patron, the Medicean stars, and they became a key element in perhaps his greatest discovery. And in a way, that's what we want to do too. We want to make movies of what's happening in these black holes. So our original target had been the center of our galaxy, this Sagittarius A star, which is close by cosmic standards. It's 26,000 light years from us. The black hole is relatively small as these things go, 4 million solar masses. M87 is 53 million light years away, and it's much larger. It's 6.5 billion solar masses. So it's a great cosmic coincidence, a little bit like the moon looking the same size as the sun, even though the moon is much smaller and much closer. It's just in proportion, which is great for us having eclipses, and in fact was crucial for the general theory of relativity, because during an eclipse you could see the stars, but the sun was there. I mean, on a normal night you can see the stars, but there's no sun. So that's a problem. And when the sun is out, usually you can't see the stars. But during that moment you could see that the stars' apparent position were bent, that the sun had bent the sunlight. And that's true of these two giant black holes, these supermassive black holes. They're the two biggest. They each carve out a relatively large region of the sky, still tiny, like a dimple on a golf ball teed up in LA, seen from here. I mean, it's not a big piece of the sky, and that's why this planetary-size telescope was needed in the first place. But so, like a dog year is 7 of our human years. Well, a Sagittarius A star minute is like a day in M87. So things, because it's so massive, a couple of thousand times bigger than Sagittarius A star, it takes a long time for things to go around it or to change in its region, whereas Sagittarius A star is relatively small, relatively near, and things change quite rapidly on the scale of minutes. So we can imagine looking at the changes that take place there. And this is a simulation that colleagues, Michael Johnson and others, have worked on to imagine what that might look like as things changed around Sagittarius A star. And eventually, hopefully, also M87. Now, this change from Sagittarius A star to M87 was not what we expected. It was really, we were thinking all the way, every time you see a mention of the South Pole Observatory, for instance, you know we're talking about Sagittarius A star because you can't see M87 from the South Pole. So that was and it was actually quite useful as a leak detector when we were trying to keep all this secret until last week. Because every time someone would say, oh, well, I think the press in such and such a country has got a hold of the image, and I'd look at the article, they'd say, oh, the German press has got it, and it would say Sagittarius A star, so that, and I didn't read any further because I knew they didn't know that we would actually switch. It was one of our secrets was that we'd switch to M87. But now, just the thing that makes Sagittarius A star difficult, which is that things change rapidly in it, offers the possibility of making movies that could be very revelatory of what's happening very close to the black hole over time that could allow us to test in a region that has not been explored the nature of general relativity and whether Einstein's theory holds up close to the event horizon. Now, nobody's made money yet betting against Einstein, but still, it would be nice to be able to check the theory in that regime. So these are the kinds of things that have gone into the imaging process. I think that this constant looking for whether there was something missing in the image, something that we hadn't thought of, was the guide star for these last 9 or 10 months. And in part, there's a record of that in the 300 or so pages of paper that we published last week, but I think it was one of the most amazing, for me, experiences that I've ever had in anything that I've done, to be able to work with people so committed to figuring out what the best argument for the validity of this image might be. Thank you.
Well, thank you for this beautiful talk. Are there questions? Yeah.
I asked without a mic. I'm just interested, you said that, well, or let me put it that way, it's not just this one image, but you showed actually 4 images of 4 different days. And this is, in fact, a movie in a way, if they contain information about what is different between these pictures. But if they are all averages, the question is, does this really tell you anything about the temporal changes? Or is it just different averages so that it is not any interest in it?
So it's a really good question. We have, well, the picture of 4 images across, I think you're referring to, is there were two from like the 4th and 5th and 11th and 12th of April, like the days right. And the 4th and the 5th look pretty similar, and the 11th and the 12th look pretty similar, but the 11th and 12th look pretty different from the 4th and the 5th. So something's changing. That's pretty clear. But what is changing is not so clear. And this bright spot at the bottom is clearly due to some relativistic motion of this hot gas, this billion-degree Kelvin gas that's circulating around it. But whether it's from the wall of the jet that's coming out of it, or whether it's got a contribution from the accretion disk that's around it, it's very hard to disentangle now, and it's one of the things that we want to know much better. One of the things that this visual study of M87 and Sagittarius A star should help us really understand is, how do these giant jets that are shot out of the North and South Pole formed? What is it that happens in detail near the horizon that allows them to collimate around these, what we think are magnetic fields, and head off in a fairly coherent way across cluster of galaxy-sized things? But whether there's something moving or something new that's being excited in the lower right from the lower left as you go from the 4th and 5th to the 11th and 12th, that really is something that's beyond what we can say now. But if you had more detailed movies, you might be able to say something about whether it's a hot spot moving around or a change in the jet or something else. So I would say, how to partition responsibility for the brightness between the accretion disk and the funnel that's leading up towards the jet or the wall of the jet is something we still want to parse with certainty. We have simulations that can help inform this, but we want to be able to get more data. And whether there's something in motion around M87 or whether it's something new being excited in the lower right as opposed to the lower left over time, that's something we want to understand better too.
Other questions? Yeah.
Can you calculate angular velocity of black hole from the image? How do you do it?
You mean the spin? Yeah. Well, it's thought on grounds that long precede the Event Horizon Telescope that the ability to make a massive jet of the type that's seen in M87 and known before EHD requires there to be some goodly amount of spin. But from the data that we have so far, we can't say, there's a scale from sort of 0 to 1, where 1 is the maximum angular momentum that it could have without violating relativity. Where on that scale it is, on the basis of what we have so far, is not something that can be determined.
Yeah.
I'm curious about the blind 4. And I'm wondering if it's coincidental that it seems that their protocol resembles a generative antagonistic network. In other words, the central paradigm of image search in AI, it felt to me as though humans were enacting that in sort of very touching social ways. And I wonder if that is a coincidence, or if they actually, in their epistemic way, are emulating their most trusted algorithms.
Well, that's a good question. I think that in a way, the blind test is something that's well known to our colleagues in other fields. Psychologists have been using blind tests and double-blind tests for a long time. So I think that, in a way, I would say that our AI is reflecting our ideas about how to conduct adversarial testing or blind testing elsewhere. And we've encoded into the AI some of our procedures that we've developed. What's not so common is doing this in physics, astrophysics. I'm sure there are examples of it, but it's not something that's fully routine. But there's so many examples of people being pushed by their theoretical expectations. To give you some idea of the way that works, is there was a famous, in the 50s and 60s, the particle physicists would do something called bump hunting. And the question was, was it a single bump or, 2 bumps? Which kind of camel was it? And that would tell you whether you discovered a new particle or not. And there were all sorts of protocols that people developed because they got burnt on this. One of them was called the A2 controversy. There was a particular case where the team had said they're 2 bumps because they wanted to say we discovered something. And it turned out that what was happening was that every time they saw something where there would look like 1 bump, they said, well, let's look and see if there's something wrong here. Let's look into this more carefully. And they'd find, you search and you find, oh, that was a day when the power was irregular at the accelerator, or this was a day when, so they kept on, they would drive their rigor on those cases that didn't confirm what they were expecting. And so they published this, that they were 2 bumps on the A2. And the Alvarez and others at Berkeley were furious that this could happen. And so what he did was to take, whenever they had data, he'd use a simulation program, a Monte Carlo, and generate random variations of the real data. And then he'd stack them up in 100 of them. And the real data would be somewhere in there. And he'd make each member of the team sort them out from most too bumpy to least too bumpy. And if the real data didn't come out on top in the most bumpy category, most too bumpy category, he wouldn't let them publish the new discovery. So this idea of intruding, it's not the kind of thing you learn in a physics course, right? Physics is not supposed to rely on things like that, but that fear of conforming to expectations in the laboratory is deep. And the famous W and the Z, for which Van der Meer and Rubia shared the Nobel Prize, there were many discoveries of the W before that were not really discoveries of the W before that. But people wanted to find this particle that would hold the weak force, that represented the weak force. And they wanted it so much, they found it. And that's what we did not, those to us looked like heads on spikes. We did not want that to happen to us.
Okay, Andy.
This is a not unrelated question. So you gave us this nice chart with the history of science for the last 300 years and how we've been...
In one cartoon.
In one cartoon, how we've been changing from century to century, from sage to worker to expert in dealing with images in different ways. I couldn't tell from your description, do you view this as progress? No, I'm serious.
No, I understand.
I'm dead serious.
So
expert looked kind of close to sage.
Yeah. So well, two things. Let me first address that part of the question and then the first part. So the expert differs from the sage or genius insofar as the expert can be trained. You don't go to Goethe school and get to be a genius. And in fact, the idea of somebody like Albinus or Cheselden or Goethe was that there were few enough of those that it never was a problem to them. Nobody said to Goethe, "Who are you to be able to say what the fundamental types of clouds are?" I mean, Goethe sorted those out, the cumulus and those. And so, there are ways in which that it depended on scarcity for that to work. In the 19th century, when you start to have a much larger scientific community, they were terrified that every, local doctor of physics in, Göttingen and London and Paris would say, "Oh, I'm just that guy you want. I'm just like Goethe. I can tell you what's really going on." And so that's why the mechanical objectivity entered. There's somebody who tended the machine accurately and with care to allow that, whether it's tracing or film photography or a million other methods that were allowed an image to go from an object to the page with a minimum of intervention by the scientist. And then that led to other problems where the expert comes in. The expert is somebody like, we can teach you to recognize the difference between a petit mal seizure and a grand mal seizure in the electroencephalogram. But it's not because you are intrinsically of a certain type. There's a program that you can, runs the textbooks and you learn how to do it. And so even if you can't make an algorithm that could do that, and there were many examples from astronomy, not just the one I gave, where sorting out star types and so on, for a long time they couldn't do that with an algorithm, but you could train people to do it. And they could do it in an incomparable way. 6 different experts would sort in the same way, even though they couldn't make a computer do it or an algorithm do it. So then the question is, so that's the difference between expert and genius and mechanical objectivity. The reason, is it progress? I don't picture this as going in sort of Kuhnian paradigms, like the old is out and then it's replaced by this. They accumulate. We still use idealizations. We still use mechanical objectivity in forms. We still use expert judgment. And in a way, what you're seeing in this image is the aggregation of all 3 into this image.
There is actually a middle ground where one can potentially have a set of templates, a library of possibilities that are consistent with Einstein's theory of relativity, and that you are trying to cross-correlate with the actual image and figure out if it's a good match compared to a random image, and then show the one that looks the best. And I should say that that is being used in cosmology very often when you have data sets that are not good enough signal to noise to actually see something, but you cross-correlate it with a library of possibilities, and then you figure out if it's real or not. So that is another approach, and would you like to comment on that and how?
Yeah, I mean, LIGO. Look, 2 things about LIGO. One is that they, at least at the beginning, they were worried that their templates might do too much, might pick out too much. The first event that they had, what was it? The October 15th or September 15th one was so loud. I mean, it was so extraordinary that it didn't really depend too much on the details of it was an extraordinary event. And, but as they become more sophisticated, now the library of templates at LIGO is immense, and they're able to make, enormously other distinctions, and now you can cross-correlate. I mean, you contributed to this area of multi-messenger astronomy, where you can learn about the event from other means. I mean, there are all these other ways that now it's embedded in a larger infrastructure, larger library, larger theoretical understanding, correlation with other methods, and I think that's given people a lot of faith that this is a real effect, and then the ability to distinguish between different kinds of objects merging or colliding.
It's a beautiful image of a black hole. I want to ask a philosophical question as to the nature of a black hole. When I made a theory on consciousness, of course, I elicited the cycle of life and death of human beings as a transmigration cycle. Now, as a black hole is a gravitational collapse of a massive star. It's the end state of aggregated matter, and by inference, aggregated mass. So by inference, it's life and death cycle of matter. What do you think of that as a concept?
In the black holes that are the mass of a star or a big star, 10 times the sun, 20 times the sun, 50 times the sun, the kind that LIGO sees, these are called stellar mass black holes, even though they can be bigger than the sun. People very much think of them as the end of a life cycle of a star's life, of a star's trajectory. And I think that that's, they used to call them frozen stars or collapsars, or I mean, there are other names for it, but this idea that in this was the end of a certain kind of matter, in a way, I think also has contributed to the broader cultural philosophical fascination that we have with these objects, that they are some kind of end state of things. Now, these very large black holes like this, that are millions or billions of times the mass of the sun, are not formed out of the collapse of a star. They're something else. And how exactly they form, whether I mean, some are surely grow by the collision and merging of smaller but still very large black holes. Some of it is dust. Some of it may be stars that they eat for lunch. But it's, they're not a single object that collapsed to make a supermassive black hole. So this remains an open question about how to think of it. But in the broadest sense, I think there is something about a collapsed state of matter. I mean, you can fall, if you went to M87 and fell through the event horizon, at least for a little while, you would be fine. It wouldn't end well, but it would begin well. And you could go through, you couldn't send messages out, but you would fall through. It's the thing that's one of the things that's so astonishing about black holes is that there isn't a substance at this boundary. It isn't a thing. It isn't a hard surface, although many people in the early 20th century hoped that it was, because the idea of a black hole seemed so repugnant to them that they hoped that actually nothing could actually get in there, but it doesn't seem to be the case.
Okay.
Yeah, I'm really glad you brought up LIGO, and I really enjoyed the cultural aspect of your talk. And I wonder if, since we all got to hear the rain down of the two colliding black holes in 2016, if maybe this is the first astronomical phenomena that was heard before it was seen. And more generally, why is it that we're not thoroughly convinced until we can actually see it?
Well, I think that, I mean, in a way, there are two kinds of knowledge that we get about whether it's the subatomic world or the very far away astronomical world. One is where we want to select a rare occurrence by our devices. And without them, there's much that we would never see. You know, many of these LIGO events we could never get if we didn't have templates. Or in a particle experiment like the discovery of the Higgs particle, there's no way you could look at everything in the old bubble chamber way. So what these selective or logic kind of experiments do is they say, if something is in our head, can we check if it's in the world by being highly selective? The danger, of course, is that you're over-selective and that you miss things, or you make an error by over-selection. The image side of things has a different advantage. It says, if something's out there, I have a better chance of finding it. Like, what if the black hole ring hadn't looked at all like what we expect? And maybe when we look at Sagittarius A star at the center of the galaxy, actually, it's going to have features of what's happening near the horizon that are unexpected from general relativity. But, so that's a different question. That's saying, if something's out there, will we know? One says, if it's in our head, can we check? And the other says, if it's out there, can we know? And the image is more in that category of, if it's out there, will we come to know it? And so it seems to me that these two complement each other in a way. They're two different ways of learning about the world, and we couldn't make do with our science without both. But that's why I think we want the image. We want to know that we haven't over-selected, that we haven't imposed this, that really we can see something and say, there is a black hole. That is where its horizon is.
Yeah, yeah.
So you worked for months and months. You worked for months and months to produce this image. How did you decide that you were done, or done enough to publish?
Well, that's a good question. I think that we tried messing up the image in every possible way that we could think of, and we kept pushing on it until we were satisfied that all these different variations of parameters and all these expert groups and knocking out different antennas. But there was always, unlike a deductive proof, an experiment doesn't terminate by an exhaustive, at some point you say ceteris paribus. And well, we did have a meeting and in Nijmegen, and I think there was a sense that we had there that we were now we set some dates about that we were going to try to hit. At that point, we were convinced enough, but that was still months before the event, and all those papers, there's 6 papers, they all had to be written, and there were frank discussions along the way about what had been shown, what were good arguments, what kind of images, what kind of analysis of those images would hold up. And I think that in the end, I think that the goal was to be pretty conservative. That is to say, like very reasonable questions like what's the spin, or was in a different category from like what's the mass. The mass depends on the size of the shadow, pretty well understood, pretty independent of model. And so we were pretty confident in saying it's 6.5 billion solar masses. But on the spin, or on the precise source of the brightness or the changes in brightness, I know many of the people in this room, I think we've had this discussion many times, I think are glad that we didn't overstep. The last thing you wanted is to have something that was going to turn out to be completely wrong 6 months from now or a year from now.
Good. So I should say that Harvard formed a black hole initiative on Garden Street. 5 of the PIs are here. And so we are really studying black hole. And Peter is doing research on philosophical questions every Monday. So you should come sometime. I hope you all support the black hole initiative. And we thank Dr. Yip for this very generous contribution to this lecture. And of course, we thank Peter for such a beautiful lecture. Thank you very much.
Thank you.